Hello, everybody. Welcome to NTWC Plus. What a show we have for you today. We're talking AI, deep learning, deep mind. It's going to be a fascinating presentation today. I think you're going to really enjoy it. We're all really looking forward to the conversation we're going to have today. Before we get to that, though, let's acknowledge the sponsors who make this show a possibility week in and week out. We start with USAA. They do amazing things for us, and we wouldn't be here without USAA. The South Padre Island Convention and Visitors Bureau. That's where we hold the National Tropical Weather Conference in person every year, and we'll be back there in April 2026. We invite you to join us in person on South Padre Island. The Weather Company, Weather Boy, and Live View, all sponsors. They're all our partners in this operation that keep us here week in and week out every Wednesday pretty much during the hurricane season. Our usual eye wall of experts is here. Let me start by introducing Dr. Hal Needham, joining us from Galveston today, where the dew point is blissfully below 80, right, Hal?
Tim, it is cold and dry. Okay, that's a bit of a stretch, but it's strangely comfortable for the summertime. We'll take it.
You don't get that very often in July or even into August. So good. Welcome, Hal. Good to see you, my friend. Bill Reed, former director of the National Hurricane Center, joining us from not far from Hal, just up the road in Southeast Texas. Good morning, Bill.
Yep, 19 miles as the crow flies inland and about 20 feet higher elevation than Hal.
Very good. Good to have you, Bill. Good to have everybody. And we'll get to our guests in just a moment. This is our 6th season, our 9th episode of NTWC Plus. We've been doing this for a long time, and it's an offshoot of the National Tropical Weather Conference. So if you like what you see here, consider joining us in person at NTWC on South Padre Island in April. Okay, Bill, let's get right to it, because I think that today's program is going to be absolutely fascinating.
Yeah. But this morning we have the pleasure of having coming to us from London, England, representatives from the team at Google that is doing AI weather forecasting challenges, and in particular interest to our group is the work they've done on tropical cyclones. I'm sure most of us have seen the news stories earlier in the season of how that plays out, and the fact that they're interacting with the good folks at the Hurricane Center and elsewhere to find the utility and best way to communicate this kind of information. I'll be primarily talking with Tom Andersson, who's the research engineer at DeepMind, where he develops advanced machine learning systems that bridge theoretical AI and real-world impact. His work focuses on scalable architectures and safe deployment strategies, helping push the boundaries of responsible AI in science, healthcare, and decision-making. And before we went on, he admitted he has the same disease that most of us have, and he's probably a halfway meteorologist by now. So welcome, Tom.
Thanks so much, Bill. Really nice to speak to you and Tim and Hal and everyone listening. Great to be here.
Right off the bat, I think most of us are probably not familiar at all with the kind of work you do and the work environment you're in. So maybe an overview of what you're working on, and then lead us into what exciting developments you have in the tropical cyclone world.
Yeah, absolutely. So I'm a research engineer at the Google DeepMind weather team. And just zooming out for a second, Google DeepMind is Google's AI research laboratory. This company has pioneered some of the early advances in artificial intelligence, like models that can learn to play games better than grandmasters in chess and Go and so on. The company recently won the Nobel Prize for building AlphaFold, which is a system that can determine and predict how protein structures behave based on amino acid sequences. So a whole mix of scientific applications and fundamental AI research. But what we're interested in the weather team is something that has become really exciting in meteorology over the past few years, which is training machine learning models on the historical record of weather data. So they start off knowing nothing, and then they essentially process decades and decades of historical weather data to see what actually ended up happening based on initial conditions. And then you can start running them in real time with data they've never seen before, and they'll produce forecasts just like an NWP system. And recently we started to specialize our models for tropical cyclone predictions. So really excited to talk more about that today.
Yeah, is the my understanding was originally, at least, that the focus and early success has been on the track forecast for tropical cyclones. Is that correct?
Yeah, absolutely. So what we found from some of the older machine learning weather forecasting results, and by old I mean about a year ago, because machine learning moves quite quickly. So about a year to 2 years ago, we were finding that these global machine learning weather models, which are trained on these historical reanalysis data sets like ERA 5, for example, they do incredibly well at getting the synoptic scale of the atmosphere. And then as a result, as you and your listeners will understand, as an offshoot of that, we end up getting really good track predictions because, of course, the track of cyclones are often dominated by atmospheric steering winds, which come from the synoptic scale. But they really lacked performance in intensity. And that's feedback that we got from the forecasting community, from the cyclone community. And we listened to that and thought, I think this is something we can solve. And that's something that we're excited to share, that we've made some really good progress on recently by specializing our models on specific tropical cyclone data sets, like from human forecasters monitoring them over the past 4 decades, and achieved a very significant improvement on intensity. So in our latest model, we've developed a really powerful intensity model as well as track model.
Wow. Do you have like an example from this year, like with any of the Eastern Pacific storms, since the Atlantic has been rather tepid so far?
Yeah, it's been a bit tepid so far. I haven't ran any analysis on the East Pacific and Atlantic seasons thus far, just because it's too small a sample size to really draw any big conclusions from. That said, we did run some retrospective analysis of our new machine learning model specialized on tropical cyclones, and found that on track, it gains about 36 hours of predictability over the European Centre's ENS system on position error, out to about 5 days. So pushing a 3.5 day level of accuracy out to about 5 days on average. And then on intensity, we did some analysis that mimicked the Hurricane Centre's verification approach, and found that we were getting lower intensity errors on something like 60 out of 70 historical hurricanes from 2023 and 2024. Which were out of sample for the model, but it is in the past, right? And we've heard from forecasters that they don't trust our models until they see real-time verification. And so that's what we did. We built this website, Weather Lab, which I'd be very keen to talk about today, which hosts our models. It's a platform that gives you an interactive map to go and click around and see the predictions and get the raw data as well, with a historical archive of predictions.
Yeah, believe it or not, I've actually played with that a little bit to get to that. What you might want to describe to people what they're looking at when they see when you're running like what the DeepMind model is putting out there, the little blue dots and whatnot, what it is and how we should be using that kind of information.
Yeah, absolutely. I don't know if anyone on your side wants to bring up the website and we could talk through it that way, or I could try sharing my screen or something along those lines.
Probably be easier to do your screen share.
All right, sure. Let me just bring that up for you real quick. So, yeah, is everyone seeing that?
Yeah.
All right, so this is the landing page that we're seeing. So it's a kind of black and white Google Maps that you can click and zoom around on, but it's showing the currently active cyclones that we have in black here. Mm-hmm. You'll notice some L's and tropical cyclone markers. So an L means a tropical low. And then this rotating marker here, Kaylee, that's a tropical storm. And then if we're into the hurricane categories, then we get a faster rotating marker with a number indicating the current category of the system. Mm-hmm. And all of these tracks splaying out from these systems are the predictions from our ensemble model. And due to inherent chaos in the atmosphere, these different solutions follow different trajectories, which you'll be very familiar with. And the actual color that you see on these tracks is, in this case, we've toggled on this feature that lets you color the tracks based on the maximum sustained winds that are predicted for each ensemble member. So actually, as we go past green, we start getting into the hurricane category status. So we have this invest system over here, and our model is currently predicting that this system, if I just click and go into a deep dive mode for this particular storm, is predicting up to probably a category 2 is the ensemble mean, just about gets up to category 2. But then if you look at the individual ensemble members, some of them are going up to just a very low end category 4 here in what is that? That's in about 2 days, 2 days and 6 hours time. So that's how you interact with this website from the landing page. One cool thing that we have on this website is that you can move up to the future here. So now all of these individual dots are showing individual ensemble members that have a tropical cyclone at that position. And once they get more and more spread out, that represents more and more uncertainty in the atmospheric state coming out of our models. So you start getting dots all over the place that may not have even originated from the same originating disturbance or system, but they may have just ended up in the same place. But you can more or less see the tropical disturbance coming off of off the coast of Africa that is starting to pick up some interest in the community. And one cool thing is that you can click this selection tool here, and you can click and drag and generate some tracks for that system to get a bit more information about what's being predicted there. And we don't have all 50 members picking something up as being a cyclone here, but you can start to see some interesting different future possibilities for this disturbance here. So that's an overview, and one of the cool things is you can go back in time. So I'll just show you Hurricane Ian from 2022. So we're going to jump back in time here. And this is what the model would have predicted if it was run in real time, but it wasn't run in real time at this point. And you can see the actual observed path in black, and then all of the individual ensemble members there. You can toggle that on and off. You can turn on a cone, and you can see the intensity that was predicted over on the right-hand side and what ended up actually happening. So I do invite your listeners to go and have a look through some hurricanes and cyclones from the past that they find interesting, and to see how we actually did. And one of the cool things, I'll just wrap up, is that you can compare how the model did compared to different systems, so different predictive models. So we have different machine learning models that we've built, the WeatherNext series of models, and we have some of the European Center's numerical models here shown as well.
Yeah, fascinating. And then when you do the verification, do you use the same conventions that NHC uses, so it's apples to apples?
Yeah, we do what the NHC calls a homogeneous verification. So we only look at the specific cyclones and forecast initializations and predictive horizons or lead times where all models predict a storm at the same time, so that it's apples to apples, relatively speaking. And when we do that, that's when we start to see that 36-hour, 24 to 36-hour lead time advantage that our model has over the European Center's ENS system. But the reason we include multiple models here is we understand quite deeply the importance of having diversity in different guidance models. So, this new model is a very powerful new tool in the toolbox, but that's what it is. It's a new tool in the toolbox for forecasters. We're not here to replace numerical models by any means. It's really important to look at that diversity of different guidance aids. And one of the exciting things is that these AI models tend to make different kinds of errors, different kinds of mistakes, which, as you average those out and look at the consensus, is likely to improve the consensus prediction.
Yeah, it fits right in with the forecast philosophy at NHC of looking at the consensus modeling approach as one of your more robust forecast tools. Now, Hal's looking like he's full of questions right off the bat here. I'm going to let Hal ask a few. He's our resident PhD, so He might ask tougher questions than Tim or I.
And Tom, I love
do.
this web interface that people can go back and look at these historical comparisons. So how far back do the historical comparisons go?
So they go back to the start of 2022. That's the data that we held out from the model. All data prior to that was used for training the model. So that's you can't use that to verify the system because it was literally trained in order to be able to predict those past events as accurately as possible. But all of these events were out of sample. And then the model is updated each year. So when you go to the 2023 data, it's actually been trained up to the end of 2022. And then the model running in real time now has been trained up to the end of 2024. So it's been trained on Beryl, Helene, Milton, and so on.
Tom, so what is the total time range on what it was trained on that time range for training?
So it goes all the way back to the start of 1979, when the Era 5 data set has its first kind of reliable data samples, coming from the advent of the satellite era really kicking off. And that's when it starts, and then it goes up to the more recent times in the present.
Tom, you mentioned a big focus to try to improve intensity forecasts. Did you zoom in on some storms that are outliers, like incredibly rapid intensification or very quick weakening? I mean, were there ways to ingest extra data to help train the model for those outliers?
Yeah, that's a really good question, Hal. So what I alluded to before is that the way we were able to achieve the breakthrough in performance of this model on intensity prediction is by training it not just on this analysis data set, which gives you these global pictures, but fairly low resolution, about, quarter of a degree latitude longitude, which is, about 25, 30 kilometers, and thus smears out the intensities, right? So that's why we couldn't trust the previous generation of machine learning weather models on intensity. So the way we overcame that is by introducing a new source of data, which is a record of hurricane track data, actually. So coming from human forecasters recording the predicted intensities from the Dvorak technique or Hurricane Hunter aircraft in situ observations, dropsondes, and so on. So training the model on that data allowed it to do much better at intensity with much lower bias. And we have looked at some outliers, so I'll just bring up Weather Lab again. Was it Oscar or Otis, the explosive intensification that hit Mexico?
It was Otis in 2020.
All right. Yeah, I mean, I would discourage focusing too much on individual cases, of course, as a scientist here, but of course they can be extremely illuminating. And one of the things is that, so this is quite early in the forecast. If I jump to a time a little bit later when I can't remember the exact sequence of events with Otis, but I do know that almost all guidance models were predicting a tropical storm to dissipate just before landfall. And this particular forecast caught the eye of some of the Hurricane Center folks and some people from the TV meteorology community as well. Brian Norcross highlighting this on Fox Weather as an example of an exciting step change on what would have been available at the time. And we actually went and showed this to some of Bill's former colleagues at the Hurricane Center. And they said, if I received this forecast at the time, it would have changed my prediction. It's not going up to category 5, but it is showing something concerning, right? It's going up to, there's some members going up into the category 4 status, and it's a landfall event, right? So I wouldn't focus on this too much, right? There are, of course, examples of forecast bust like there would be with any model, but this is something showing you the potential indication that the model is picking up on something that the existing physics-based models or hurricane models wouldn't have been able to pick up on at the time.
Well, Tom, that's a good point. And even if people are primarily looking at physics-based models or numerical models, at least seeing this from a different angle, right? It might make them take a double look and maybe investigate further and not dismiss a storm as weakening or tracking off the coast if they saw something like this.
Exactly. Yeah, that's one of the things we're really excited about here. It's just adding a very powerful new tool in the toolbox that gives forecasters something different, something that is a completely different paradigm. We're not building these models by trying to code up the laws of physics from scratch. we're training the model on what actually happened in the past. And by doing that, it's able to overcome some of the biases and limitations of numerical weather prediction. And of course, introduces new caveats, like it doesn't necessarily respect the laws of physics. So it won't necessarily conserve energy, momentum, and mass precisely. But what we do see is that the results kind of speak for themselves in the gains in performance that we're able to get on average.
Tom, I've heard of professionals in computing describe that AI just does, and machine learning do amazing job at pattern recognition, ingesting tremendous amounts of data to explain what is happening. And someone's explained to me more like these physics-based models more tie in why it's happening. Is that an accurate way to look at this field?
Yeah, I think that's fairly accurate in the sense that physics-based models, to a certain extent, can be understood because they've been created in a very explicit way by human beings. In some sense, I'd push back in that there are many parameterizations that you get in numerical weather prediction systems due to the unresolvable processes below the grid scale that's able to be computationally modeled by the supercomputers that run them, like the global models tend to go down to, I think they're 9 kilometers at the moment, is some of the best that we can get. And essentially, we just need to look at past data and fit some formulae that capture the behavior of clouds or whatever it may be on the atmospheric state at the model resolution. And in a way, that's a kind of machine learning as well, right? It's just not talked about in that way. With machine learning, there are ways you can try and understand why the model is predicting a certain thing, but I can't give you analytical equations. I can't write down on a blackboard some equations for what it's doing with the atmospheric state to arrive at a solution.
Thank you, Tom. That's a very helpful description for our listeners there. I really admire the work that you and your team are doing. Tim, I wanted to pass it over to you. Have we had any questions come in? I know sometimes people send questions before the broadcast.
Yeah, we do have a viewer question. Thanks, Hal. And this is a fascinating discussion. It's been fun. And my questions are going to be a whole lot simpler when I get to those. But let's go to the question came in from Casper. And he wants to know, are there any websites that document the accuracy of the DeepMind model compared to the legacy global models?
Yeah, great question. I believe Casper was asking the question there. Thank you. So, what we've done recently is we've released a model called GenCast, and that was our team's previous generation, our previous model, which is running operationally under the name Weather Next Gen, which anyone can sign up to access. And we had a Nature paper out verifying that against the European Centre's ensemble system, ENS, with a whole host of meteorological verification going on there, as well as some cyclone tracking specific stuff, both paired track error when you look at active storms, but also looking at how well the model captures the probability of a cyclone being in a particular location at a particular time, which includes cyclogenesis verification. Now, looking more recently on our team's work, we've built a new kind of machine learning model, which uses a different type of algorithm than GenCast. This model is called FGN, and we put out a paper, the team, onto arXiv recently. So if you look up, the paper's called Skillful Joint Probabilistic Weather Forecasting from Marginals. So a bit of a word salad, so I assume viewers might have to play back and write that down. But Skillful Joint Probabilistic Weather Forecasting from Marginals, that describes our new type of system, including verification against GenCast, because GenCast outperformed ENS. So GenCast was then the new state of the art. And FGN actually outperforms that even further. So we then specialized FGN to predict cyclones in the way that I was describing earlier, training the model on this tropical cyclone-specific track data set. And we've got some verification results in a blog post about Weather Lab. So if you look up Google DeepMind Weather Lab, you might see a blog post from DeepMind that includes some of our verification results that mimic the National Hurricane Center's verification strategy, comparing with Hurricane Regional Model HAVSE and Global Model ECMWF ENS there.
I think the fascinating thing about this whole, machine learning thing is the speed. We have to change our mindset about how fast things happen. You see something happen a long time ago, and we're talking 12 months ago, versus in the world we live in now, a long time ago is 10, 15 years ago. So we're learning so quickly.
Absolutely, and that's something that we've found speaking and learning so much from the meteorological community. Learning from folks at the Hurricane Center. We've also been working and speaking with people from the UK Met Office and so on. And we go to AMS. We're meteorological nerds really, but we're not real meteorologists, but we like to think we are, and learn a lot from meteorologists. And the thing that I think is surprising to people from the community is the pace of advances. And just to put that in numbers, Bill, you might be able to check me on this, but if you look at the Hurricane Center verification reports, as well as other studies out there, there's a rule of thumb that physics-based weather prediction has gained about a day of prediction skill on predicting the track of tropical cyclones once per decade. So you get about a day per decade of prediction accuracy. Is that right, Bill?
That's what we use. I mean, when I first started out, back when electricity was invented, you were lucky to get a year where you had a 24-hour error of around 100 miles.
Exactly, and we're standing on the shoulders of giants in every sense of the term, in how far we've come since then. I actually think it's one of the greatest achievements of humanity, putting out this vast observing system with so much technology and building the algorithms and systems and computers to simulate them. So it's really amazing, and how many lives that's saved. But one of the things with machine learning is that we're starting to see more rapid advances, because these algorithms can be tweaked and improved more quickly than the existing physics systems. So gaining 36 hours of lead time advantage over ENS is quite a breakthrough, I think is fair to say, because it corresponds to over a decade of research advances. And this is all done within the space of a couple of years, depending on how you measure it. So it's quite an increase in the pace of improvement that we're seeing.
Let's take a break from the current conversation. It's fascinating and it's moving rapidly. Let's go old school, Bill, for a minute, and Tom will give you a break for a second. And Bill, give us a tropical update in the traditional sense of the word. Tell us what's going on. I know the Atlantic's quiet, but the Pacific is not.
Wow. Yeah, Timmy made it sound like I was going to come on with a Ouija board.
You have that under the camera lens. I can see it, yeah.
All right, I'm going to pop up the screen here and find what I wanted to show. And it'll be a mix of old school and new school. I was having trouble downloading my favorite satellite images, so we go back to Weather Nerds, run by a gentleman that's at the Hurricane Center, or at least was the last time I knew. Overview of the tropical Atlantic. There's convection with a frontal zone that's been persistent out here that occasionally models seem to want to hint at, but not so much this morning. A convection-starved wave out here in the tropical Atlantic, another one over here heading westward. Again, the models so far have been fairly tame on anything with this. This is another one of these upper-level features that actually is rotating around the big dome of high pressure that's giving us the heat wave that everybody's moaning and groaning about. And they should, because people lose their lives in these heat waves. And much to my dismay, the rain gets within sight of my yard and doesn't fall on it. As for the Atlantic forecast, we'll come back to that picture in a second. The updated version of the outlook is the one we like to see. Nothing expected in the next 7 days. Not so. The same case is not it's not the same case out east, out in the Eastern Pacific and into the Central Pacific, which I'll go to next. This is probably going to be the next storm up in the Eastern Pacific. 80 to 90% chance of development. It's not there yet. It's still getting its act together, but there's a lot of convection and no signs of wind shear or dry air, and it's over extremely warm water, anomalously warm, for above even what's normally more than conducive for development out there. And then we have our really active. It's typically it's an El Nino pattern that sets off the Central Pacific into more activity, but we're in a cool neutral phase right now, so this is highly unusual. Iona, Kelly, the next disturbance in line in its wake. And it's a long-term subtropical high has been inducing a west to east to west steering current, and the systems that come off Central America and Eastern Pacific without developing have reached a favorable environment as they pass 140 east, which is the demarcation from East Pacific into the west. What are we looking at on the east? There's more than I can even show you here. It all bunches up, but there's Iona, which is in a weakening phase, Kelly, which is in a dying phase, well south of Hawaii. Iona's supposed to stay tropical storm. Last I looked, for at least 4 or 5 days now, as it leaves the Central Pacific and into the Western Pacific. Be interesting to see if it holds together there. The next disturbance is given a 50% chance of developing, and then the orange here is for something that's not on the horizon yet, but will be coming off Central America by this weekend to watch. And then we've got 99E here, which is the next most likely developing storm in the state of things we're looking at there. I like to look at what Mr. Toomer puts out for graphics. They had a little bit of everything on them. So here's the latest forecast with conditions on it of these two, and then the outlooks. And I like the underlay of the sea surface temperatures. The graphic, it makes it easy to explain why it develops and then dies. It's heading into cooler water and usually drier air as it gets farther north in the Eastern Pacific. Let's see. Not to be outdone, I have a weather lab up here, and the example here when we get to a hurricane mode on the model forecast there, and get it out a little bit there, and then as you can see, it brings it up to at a peak. It gets up to a category 2, and I didn't know about the deep dive aspects. So while you were talking, I popped that up there. That's a very good way to look at the wind and pressure aspects in the forecast in there. I think I have one more slide here before we get back to what everyone's interested in. There we go. Our friend Michael Lowry had a very nice discussion on what's going on with the SAL. We had a lot of SAL in the early part of the right before the start of the season. We had some anomalously high volumes of dust coming out, but since then it's gone quiet, and there's virtually nothing going on in the dust world today. And he didn't really go into what that bodes for the future. I think that's still a subject of research, but at least for now, that doesn't seem to be an inhibiting factor heading into the peak of our season. And I think I'll stop sharing for now. Looks like Tim has a question.
No, this is fascinating. It's to see the Pacific so active, so many things going on, and the activity south of Hawaii, of course, they're dealing with other issues at the moment, which I'll bring up in just a bit. But let's do our midway break and thank our sponsors who are here again today. USAA. Thank you, USAA. You know, we've been doing this stuff for a long time. Alex and I have been doing stuff, and Bill and Hal have been in for a long time, and USAA has been in from the very beginning, and they really support what we're doing here. They support resilience and preparation. We thank USAA for all that they do. The South Padre Island Convention and Visitors Bureau, we mentioned that's the host of the conference. We are there. We'll be there in April again of 2026. We'll be at the beautiful Marriott Courtyard Hotel right on the beach next to the big pier, and should be hopefully a good week to be out there. A lot of learning to be done, so we invite y'all to come join us for that. The Weather Company, they provide weather graphics to TV stations all over the country. Weather Boy, they provide scholarships to college students from anywhere in the U.S. to come to the National Tropical Weather Conference, an all-expenses paid trip to come and sit next to Bill and Hal, whoever's there, and just learn about tropical meteorology. And LiveView, they let all the broadcasters broadcast back to their home markets so they can show where they are at the National Tropical Weather Conference. Hal, let's talk GeoTrack for a moment. What's going on in GeoTrack this week? We haven't gone there.
Yeah, thanks, Tim. With GeoTrek, we're exploring the world to bring you stories about extreme weather and natural disasters not covered by the mainstream media. We pulled out the big guns this time. We went to find a world-famous meteorologist, our very own Alex Garcia, chief meteorologist at Fox 29, joined us on a conversation about the catastrophic flash floods in Central Texas over Independence Day weekend. It was really interesting. Alex explained the science behind the sudden and violent flash floods in that region, and also what we can do to reduce loss of life and property moving ahead. A few things I got from our podcast. Number one, he really made the point that if you take those heavy rains that happen in the hill country and you move them to, say, Beaumont, Port Arthur, or South Louisiana, where you have sandy soil or a different soil type, you would have had a different response in the flooding. It's that limestone, the hard rock there in Central Texas. It doesn't take much rain to get extremely fast runoff and high rises in the rivers. Also, you have a lot of topography out there. So even, 2 or 3 inches of rain in a short amount of time, you're going to get very quick runoff, and that's going to produce some catastrophic flooding. Alex also talked about really no matter how well we forecast these events, if the communication is not getting to the public, we're still going to see threatening loss of life and property. And so we were talking on the podcast, and he made the really good point about making sure you have multiple ways to receive watches and warnings. And we talked as well about NOAA weather radio. We know a lot of people, when you get in topography, they go on a hillside or near a cliff, their cell phone might not work. They may not get that warning on their cell phone, but NOAA weather radio signal, it does not depend on cell phone towers. And so it's probably going to get to you and provide that life-threatening warning. So a great podcast there with Alex, amazing insights. That post wherever you listen to podcasts, Apple, Spotify, it's GeoTrek Podcast 116, and it just released yesterday with amazing insights from Alex on the flash floods in Central Texas, how we can better prepare for events like that in the future moving forward, and just some insights on how we can better communicate watches and warnings.
Thank you. Appreciate that. I know that Alex guy. He's pretty good at what he does. He's the real deal. So
Tim, I have to say, he has a very calm and clear way of explaining even the most complex or, very intense topics. So I think I've already gotten feedback. Our listeners are really enjoying his perspectives on what happened in Central Texas.
That's terrific. And that's why he's so successful in this business we call TV weather. So we appreciate that. Hal, I'm surprised that you're not on an airplane to somewhere in the Pacific, which, to somewhere, as we're recording this, we're of course dealing with tsunami warnings on the West Coast and Hawaii and places like that. Are you going to go anywhere?
Tim, I promised myself this week I was getting to bed early every night. And then we saw the tsunami coming out of Russia last night going to Hawaii. I stayed up after midnight Central Time. My early work before hurricanes was working with tsunamis, earthquakes, and volcanoes in Alaska and Hawaii. So I had some experience out there. And just, it was amazing how engaged people were on social media. Obviously, we were watching the huge tsunami potential, especially for Hawaii, also parts of Alaska and the Pacific coast. I was just amazed to see just the monitoring systems as we have buoys out there and the science behind monitoring, tracking these systems. Again, the concern was for a massive tsunami to sweep across the Pacific last night.
Fascinating to watch. I was with you. I was sitting here staring at the computer until well after 1 a.m. Central Time, just waiting to see, which takes me to my next question for Tom. And I know this may be a little bit sideways because I know we're not necessarily weather, and maybe you can kind of steer us for maybe a future show. But, I was watching the broadcast out of Hawaii at 1 o'clock in the morning, our time, and they're all watching the ocean, and they're all saying that wave's coming in at, 7:10, and 7:10 hit, and there's nothing. A little tiny, and I think I see a wave off in the distance. They didn't see anything. And, based on that forecast, it was going to be there at 7:10 p.m. And of course, it progressed over the night. They finally started talking about that. But is there AI learning and is there modeling now for tsunamis following earthquakes like that? Is that something we're getting into as well? And again, you can steer us where we need to go if that's the case.
That's a great question. I don't actually know of tsunami prediction machine learning systems, but I mean, what I've heard from looking at some of the news of this quite concerning recent tsunami was that it's extremely complicated to model the ocean's response to that seismological event, and then to handle the really fine scale coastal features which can influence the actual threat to coastal communities from tsunamis. So I know that it's a difficult problem. I know that the ocean is a more mysterious beast than the atmosphere just due to the lack of observation measurements that we have, which is kind of how we've been able to unlock powerful gains in predictive performance in the weather space with machine learning, because that vast volume of data has been able to pin down the atmospheric state over time fairly reliably and allow us to train the model to get some quite useful signal on what actually ended up happening. With the ocean, it's just a different kettle of fish. I don't know if that's a pun, if that's a British phrase, but it's go ahead.
Yeah, I use that all the time.
Nice, yeah. I guess it's a pun. But with weather, it's different. And I think what I want to draw us to here is that when there are communities and lives under threat from a potential serious environmental hazard, whether that's a cyclone or a tsunami, it's really important to have these official voices giving a single view on what the latest science and information technology is saying, that is extremely conscious of the way that people respond to those threats, because false alarms can lose trust. And I know that's something that the Hurricane Center has to contend with, just balancing that risk of the false alarm versus the false negative, right? The threat of people being unprepared. So that's why we've been really honored to partner at Google DeepMind with the Hurricane Center with an official NOAA CRADA, Cooperative Research and Development Agreement, for a legal contract for a public-private partnership, where we've outlined how we're going to work together. And we're going to, the Hurricane Center has been looking at our real-time predictions this season, and they've mentioned it in a few of their hurricane discussions in this season already, the new system that we've built. And, it's really beneficial from our side to know that we have that interface of human forecaster experts who are plugged into the wider emergency response community in the United States. And it's a global product that we're building as well. So the Hurricane Center has proved itself amazingly open-minded to new technology. But, it's a global product and the data is available for download globally. So we're also excited to work with weather agencies around the world. But we're very keen to emphasize that we're not here to replace those agencies that have been in place for decades and have been doing an excellent job in that time.
Not just another voice in the darkness, but a partner with the experts. And that's terrific. I love that. One more question, then we'll get back to Bill and Hal. We talk about the speed at which this is evolving, but what about the speed of the runs of the models themselves? It takes time for the European model or the GFS model or whatever, the HRRR, to put out a forecast run. How quickly are your models, your AI machine learning models, putting out a forecast?
Yeah, that's a very good question. Our models run much more quickly than physics-based models, as you might imagine. Physics-based models need to solve these very complicated coupled differential equations that run on supercomputers the size of a bus sometimes. In contrast, machine learning models run on these tiny chips called graphical processing units, or GPUs. At Google, we have to be different. We call them TPUs. We have our own chip that we use here, but it's the same kind of thing. And one ensemble member from our latest model takes about a minute to produce a 15-day forecast. So that's in contrast to some of the big, bulky physics-based global models that can take hours and hours on a supercomputer. So a speed up of conservatively hundreds of times, potentially up to thousands of times, which, as a kind of way of measuring that, is roughly the difference between Usain Bolt at his top sprinting speed in a 100-meter race and a garden snail moving at a garden snail pace. So it's really fast, and that opens up some opportunities for potentially large ensembles, right? If you can generate an atmospheric prediction so quickly, then you can generate many more of them in a reasonable time frame so that the forecast is still relevant. And I think it remains to be seen how useful these potentially large ensembles would be for downstream applications and extreme weather. But extreme weather is unlikely by definition. And so I think that's a pretty exciting avenue forwards that we can get from this fast speed of the models.
Terrific. Bill, jump in.
Oh, wow. Where do I want to start here? Okay. Keeping in that frame on the time frame, we've learned that it's very fast running. When do you actually initialize a run? Is it tied at all to the run cycle of the numerical models?
That's a really good question. So actually, the latest model that we've built is completely dependent on the European Centre's atmospheric initial condition snapshots. So our models are still heavily dependent on numerical weather prediction systems in that regard. The data assimilation algorithms that they run from tens of millions of observations to initialize, and we initialize from that as well. So we have to wait for then, and then it's very fast.
That leads me to another question that I've always, how you got the rapid refresh and whatnot on the smaller scale models. Say we have a run cycle. You've issued the run. The forecast is for the storm to intensify, but not rapidly. And about 2 or 3 hours into it, it's gone off the roof. It's rapidly intensifying. Can you adjust the initial conditions and run another AI run on it at that point, or is that still something that you're stuck with the initialization from the standard times?
So the existing model, the primary source of data that it receives to initialize its runs is the atmospheric state, which obviously wouldn't have updated in that time frame during which the rapid intensification would have occurred. But one of the really hot topics in the machine learning weather space, which I think is driving quite a lot of the innovation around the future generation of these models, is operating directly on raw observational data like microwave, satellite sensors, scatterometers, and these satellite pictures that are able to actually detect this rapid intensification. And if you go off that, then you can potentially reduce the latency significantly and get something that you could call continuous forecasting, where every 10 minutes or whatever you want to call it, you get an updated forecast, which would be quite a different paradigm to what we've been able to achieve with existing global models that tend to be every 6 hours.
Yeah, I can see some real advantages, especially when you have a storm that's within the 24-hour time frame of a landfall, and it goes off the forecast out there. The ability to have some guidance to go along with the observation when you update would be useful. One of the things that the Weather Enterprise in Europe and here have focused more on in the last decade or so is focusing on the impacts. So, for example, with a hurricane, the size, how big the wind field is, how strong the wind field is, the storm surge and rainfall. Does your model? Are you working towards forecasting in that sort of environment also?
We're increasingly interested in expanding the types of variables that our models are predicting to be more and more useful for impacts. Our model does actually predict cyclone size and the wind radii fields at 34, 50, and 64 knots. So if you go and look in the raw data of our predictions that we're releasing with Weather Lab, you will actually see those fields. The reason we haven't shouted from the rooftops about it is that the wind radii are a lot more uncertain than the track and intensity variables of cyclones. So we're a bit less confident in them. So that's an active area of research, and we're excited to keep working with the Hurricane Center as they start to verify these predictions for size. But of course, that actually dictates where gets hit, right? It answers that question. I don't care where the eye of the storm is going to go, really. I want to know if my house is under threat and if I need to evacuate. So you're really right to bring those things up. And also, wind isn't the only dimension of threat that a hurricane can produce. Of course, it's also storm surge, it's also flooding. So that's something that we're increasingly interested in going forwards.
Great. That's good to know. How many staff members do you have working on the Weather Lab part?
So It's hard to say exactly, and one of the things that is exciting with machine learning is often you can get quite big advances with relatively small teams. So I don't know if I can give an exact number, but it is probably going to be smaller than you'd expect, because often the code bases that we're working with to process the data and the model itself is a lot smaller than the existing physics-based models. So I've heard some numbers thrown around, like some of the global weather prediction models are over 1 million lines of Fortran. So the order of magnitude that we're working with is much smaller. That doesn't mean it's not hard, and we don't work very hard to try and build systems that are as useful and trustworthy as possible for our users. But it does mean that you can get more bang for your buck, essentially, in terms of headcount.
Interesting. So say I take a trip to London in the next year. Are you guys open for visitors, or are you all working from home and it wouldn't matter?
No, yeah, we're back in the office now after COVID has thankfully reduced in its impacts in the UK, as it has all over the world. And so yeah, we're really happy to speak to people from the meteorology community. I personally would very much welcome speaking to you, Bill, in person, and Hal or Tim, for that matter, if you come to London. So yeah, definitely let me know if you're in London.
Well, maybe one of us will win the lottery and we'll all fly over there and do the show from there.
That would be awesome.
Let's see if I've got all those. I had another question there. Nope, I did them all. Hal, what you got?
Yeah, Tom, I have two last questions for you. When you're training historical data sets and you're looking what, maybe a storm did in a certain region, can you underline an estimate of the sea surface temperatures for that year? I mean, do we have data on that to kind of look for relationships there, or is that not really explored as much?
That's a really interesting question. We haven't looked into that ourselves. Our model does receive sea surface temperature from the data assimilation kind of boundary condition snapshots produced by the European Centre. So I do think, I have a hunch that the model is using that in its predictions quite heavily. If you look at that, what's the storm, 99E, that's just moving northwest in the East Pacific right now. Why is it predicting a hurricane category 2 status in a couple of days? Well, I mean, I'm sure it's using the sea surface temperatures alongside how conducive the atmospheric state is to intensification. But that's something where I would love to see the community download our historical archive of data and find that out, because that would be really interesting.
I love how open source it is, that people can kind of take these data sets and run with it and play with that. I know a lot of our listeners are interested in that kind of thing. So that's pretty amazing. Tom, I wanted to also ask you, what advice do you have for our students and our young professionals who say, this is amazing, I want to study this, or I want to work in this field? I mean, what advice would you give them moving forward?
Yeah, well, I mean, the machine learning for weather research field has really picked up in recent years. I've been in this space for around 5 to 6 years. And back then, it was more like the kind of thing where you'd have a kind of hushed conversation in a corridor, like, oh, I think machine learning algorithms could do well at this. And then you have the naysayers. And of course, there's still caveats that remain about these models. But if you go to a big conference like AMS, the American Meteorology Society, you'll see many posters and talks and panels about the opportunities of machine learning. And I'd say there's a lot on the internet out there to explain how machine learning algorithms work. If you are interested in maths and physics and computer science or any of these fields, then there's a lot of transferable knowledge, because machine learning is it's kind of like an engineering science with a lot of mathematical fields underpinning the algorithms. So like linear algebra, calculus, and probability theory are some of the main ones, and optimization as well. And there's loads of ways that you can pick up machine learning algorithms from the internet and try and train them on some data. And I think this field really benefits from having domain experts as well. So fans of the show who bring more of a meteorology background would be really welcome in this research space.
Thanks so much, Tom. Really, really brilliant, the work that you all are doing there. Tim and Bill, I wanted to pass it back to you as we're getting closer to the close.
I just want to see, as we get close to the end, what do you see in the future? We've come so far in the last 5 years, from whispering in the hallways to putting it out to the world on the web. Where do you think we'll be in the next 5 years? What's in the future?
Well, I think we're going to continue to see increasing performance gains from these machine learning systems. And I predict the existing physics-based centers are going to continue to adopt these algorithms in their own operations. We see that with the European Center doing great work with their AIFS system that some of your listeners may have heard of as well. NOAA's starting to pick up more machine learning algorithms in-house as well. And I can see a field where we have quite a diverse mix of physics-based models running alongside machine learning-based models, and they're going to offer a mix of different pros and cons. But I really do anticipate increasing performance gains on the machine learning side, and potentially interesting hybrid systems as well. Just to talk about something completely different is climate prediction. And I think one of the exciting things with machine learning is integrating it with physics to ground it in some sense, but being able to run the model much more quickly. And we have some colleagues at Google Research doing that with a system called neural GCM. So it's a neural network general circulation model that can run much faster and potentially produce many more different scenarios for the future, capturing different tipping points, potentially capturing these unlikely events. So yeah, I do see some really exciting things. And I think the way the Hurricane Center is using Weather Lab in our system operationally now in an experimental mode, I'd like to see it go into the official consensus aids and going into informing the official forecast more and more so that we can help on the mission of saving lives and property.
Rapid intensification of what we're learning. I would love that. That's so cool. We're all familiar, Bill and Hal and I are all familiar with the website. We've been there, we've messed around with it. But for those who aren't, what's the website so people can go find it?
Yeah, I could. If you search Weather Lab online, Google Weather Lab, then that'll be the easiest, least error-prone way of finding it. But the URL, I'll maybe just say it twice for listeners who want to type it in. So it's deepmind.google.com/science/weatherlab. And maybe you could put it in the podcast description as well. So it's deepmind.google.com/science/weatherlab. And we really welcome feedback. We have a feedback button at the top right. It's like a little chat thing with an exclamation mark. We read everything that people say. And if you like it, please tell your friends about it. This is the reason why we do this is because of the great feedback that we get.
I feel like we need to take a break and come back for the second hour of the show, but there is no second hour. It's going to go on for a while. Hal, what do we learn today as we wrap this up? Hal, what's your takeaway?
Yeah, it just gives me hope. The more angles we can look at these storms and predict them, the better. And I love just to see the progress, how rapidly evolving this field is. It gives me hope of different angles to look at these storms in the future. Great job to Tom and your team, and I'm excited to see where this goes in the future.
Amazing. Yeah, thanks so much. Just final word from me is we're standing on the shoulders of giants, as I've said before. I'll say it again. We're really grateful to how open the weather community has been, and it's an honor to be able to give something back. So thank you, and thanks to the three of you for having me. It's been a really fascinating conversation.
We appreciate it. Thank you so much. And Bill, do you have a last word before we shut this down?
Yeah, I had one takeaway I had. We were talking about what future work people ought to be, new people coming into the field or on it or already in it. Seems to me that since this relies on the data assimilation, that continued strong physical research on making the best possible data assimilation to start with is going to be one of the keys to continuing to improve in the resolution of any kind of model, but especially these. And notice Tom is nodding his head. Actually, I want Tom to give me an AI forecast for what the odds are of Tommy Fleetwood winning the Open next year.
I have high uncertainty in my prediction because I don't know who Tommy Fleetwood is.
I thought you would. He's an English golfer, and he's always close, but never quite the winner, and I liked his style.
There you go. And I'm just curious about how I can get one of those TPU chips implanted back here somewhere so that you just ask me the questions, I know the answers. I want to get there at some point. So
I'm not sure. I'm not sure you want that, but some people are looking into that, like Neuralink with Elon Musk. But we'll see. We'll see how that pans out.
Well, Elon lives right down the street, so I'll go down there next in just a little while. So, gentlemen, great program today. Thank you so much, Tom. Thanks for being with us. We really appreciate it. Fascinating information. I would love to do this again in a year and see how far we jump from this year to next year, because I have a feeling it's going to be a lot. Thank you, Tom.
That would be awesome. Yeah, great. Thanks for having me. It's been a really awesome conversation.
Let's thank our sponsors who make this program a reality week in and week out: USAA, the South Padre Island Convention Visitors Bureau, the Weather Company, Weather Boy, and LiveView. Thanks to our host, Hal and Bill. Thanks, Tom, for being with us. And thanks for being part of NTWC Plus. We enjoy being here. We'll be back soon with yet another program. Thanks for being here. Bye-bye.